Okay. So I guess last class we covered quite a bit, and I think you all understood well in the last class. Any questions, any doubts, confusions in the last class before I start the solubility criteria? Everything is okay, clear on the eigenvalues? Yes, please. See, basically, generalized eigenvectors occur when we have decreased eigenvalues. Okay, as I said, eigenvectors form the basis if the distinct eigenvalues are possible. Okay, of course, non-symmetric matrix eigenvectors are not orthogonal. Okay, but we have proved that they form the linearly independent basis. And from the dimensional orthonormalization, if we have linearly independent basis, it is possible to construct orthonormal basis. And with that, we can actually still work on the orthonormal basis in the thing. But once you construct orthonormal basis, that cannot be used as a good basis like eigenvectors. Because you know that when you solve x equals to b, and when you write x vector, a summation alpha I require eigenvectors, and you put it at a and lambda I, that kind of mapping will not be possible if it is orthonormal. So it is always possible. So in that case, we can ask me that if it is not orthonormal, if it is not eigenvector, is not a good basis, but it's still with the linearly independent eigenvectors, it's possible to work with because we have the complex conjugate eigenvectors, and those eigenvectors will go orthonormal. So you have done all those things last class. Okay? Any other conclusion? It's because what I actually tell you that many things I don't write in the board, and it's my experience in the student life when I was a student, even in my bachelor's and master's and PhD, whatever course actually I used to take, I used to write very fast. Whatever prof will tell, I will write. In fact, because profs will not talk much, will not write much in the board. But if you just follow, get the quick notes, you can see we have entire book with it. Because so many things I'm talking, even things are not in the books. So, but many of you write only I did write something in the board. In that way, you'll be missing a lot of interesting philosophical perspective what I discussed. Okay, so we are talking about the solubility criteria. Let's talk much on that, and let's see what we are learning. So we have seen that the first statement, if AU equal to 0 has a trivial solution, then AU equals to B has a unique solution. If A equal to 0 has a trivial solution, then A equal to B has a unique solution, and it has been proved already. Because you say U1 minus U2 equal to 0, then U1 equals to U2, and that solves the problems. Okay, so next question, next topic on solubility criteria. If AU equal to 0 has non-trivial solution, and then AU equals to B may or may not have solution. We have seen it in the range space. We have seen that rank of A equals rank of A augmented B to get the solution. If it is not a solution. But we are actually proposing a theorem called Fredholm alternative theorem. That we have not given the statement. Did I give the statement of Fredholm alternative theorem? Okay, so we'll be doing it. So it says that if so for any of the system, so AU equals to F. If I have a problem, AU equals to F. A is an operator, the matrix operator. A matrix. We use a vector. F is a vector. So it is possible to construct something called adjoint problem, which is L star B equals to 0. L star is adjoint operator. L star is adjoint operator. B is the corresponding vector for the solution. And if inner product FB equals to 0, then we can say the system is solvable. So this is nothing but Fredholm alternative theorem. This is called as Fredholm alternative theorem. So AU equals to F is the main problem. You have to construct L star B equals to 0. So I will give an example on this. And if inner product B equals to 0, okay, If inner product is not inner product is not equal to 0, then you don't get the solution. It has to be 0. So this criteria, we like to see whether it matches, and let's see what actually happens. So for our problem, so we have AU equals to B. For our problem, we have AU equals to B. Okay, and what is the solvability criteria? Solvability criteria, it should be A star B equals to 0 is the adjoint problem, and the criteria is inner product BV equals to 0. The criteria is inner product BV equals to 0. So how to prove it? Always you have to go for proof. How to prove it? So we can write BB is nothing but AUB, inner product AUB. Okay, and we have seen. Okay. So this is the adjunctive, right? So AU equals to B and U A star B. Okay, and this is my problem A equals to B. So from here we can see this BB, and it is nothing but U A star B, and A star B equals to 0. So we are taking a vector, the inner product vector, one vector is 0 vector, and it has to be 0, not a vector. So this is nothing but inner product BB equals to 0. So and of course it follows that for this case rank of A equals rank of A augmented B, and that you can actually prove. If BB equals to 0, you can actually say that rank of A equals rank of A augmented B. So that was the quite sort of logical proof, but this is the rigorous mathematical proof, inner product BB equals to 0. So now, after talking about this, the right time to look at the assignment problem. The problem number 3, problem set 3, the last problem obtains a solvability criteria of the following system. U1 plus U2 plus U3 equals to V1. Let's look at the assignment problem. Last problem, assignment. Last problem, assignment. U1, problem set 3. Problem set 3, problem number 7. U1 plus U2 plus U3 equals to V1. 2U1 minus U2 plus U3 equals to V2. And U1 minus 2U2 equals to V3. U1 plus U2 plus U3 equals to V1. 2U1 minus U2 plus U3 equals to V2. And U1 minus 2U2 equals to V3. So, we need to verify or we need to get solution. So it says that obtain a solvability criteria for the following system. So we have to have the adjoint problem, of course. And first, let's look at it satisfies AU equals to 0. Okay, AU equals to 0. It has to satisfy the second problem. So is it possible? My question is it possible to construct this kind of problem A equals to B? Of course, yes. So we have the matrix 1, 1, 1, 2, minus 1, 1, 1, minus 2, 0. U1, U2, U3 equals to V1, V2, V3. Okay. So first we have to see that what is the situation here, whether the determinant of A equal to 0 or not. Okay. So how to proceed? Determinant of A equal to 0 or not? We don't want to calculate it. We will go by echelon, right? We will go by echelon. So if you talk about the echelon form, this has to be 0, this has to be 0. So R21 should be equals to R2 minus 2R1, R31 equals to R3 minus R1. So we get 1, 1, 1, 0, and then minus 3 minus 1, 0 minus 3 minus 1, u1, u2, u3, and equals to v1, v2 minus 2v1 and v3 minus v1. And if you see that, one more step you do that, and this will give 0. One more step. I don't want to do that. And it says that determinant of A equals to 0. It says that, so from here, it is concluding remark is determinant of A equals to 0. Concluding remark, determinant of A equals to 0.
Sir, dust is there.
Okay, sorry. So, if determinant of A equals to 0, that means what? If you do A star B equals to 0, it also says determinant of A star equals to determinant of A, we have already learned it, equals to 0, and we should give B bar non-trivial. Very interesting. You get B bar non-trivial. Okay? And for this case, it is very much challenging to prove, to see that condition inner product BB equals to 0 for the situation, and we will see that it actually follows our range space calculation. So if you know our range space, we can see this argument will follow the range space argument. So what is your A star? So A star B, when you want to calculate, A star means 1, 2, 1, 1, minus 1, minus 2, 1, 1, 0, V1, V2, V3, 0, 0, 0, correct? Okay. And now R21, which is R2 minus R1, R31, which is R3 minus R1. And how much we are getting? 1, 2, 1, 0, minus 3, minus 3, 0, minus 1, minus 1, V1, V2, V3, 0, 0, 0. Okay? And then what actually happens? If you look at this minus 3, minus 3, minus 1, minus 1, and of course, you have to do another step, which is R32, which is R31, then it should be minus R21 by 3. Am I correct? Yes. So which is 1, 2, 1, 0, minus 3, minus 3, 0, 0, 0, V1, V2, V3 equals to 0, 0, 0. So these are the two independent equations based on our rank of the matrix. Okay? These are two in the echelon form. The non-zero rows will give the independent equations. Okay? And what are the equations? So first equation will become 3v minus 3v2 minus 3v3 equals to 0, and it will be v2 plus v3 equals to 0. Another equation is v1 plus 2v2 plus v3 equals to 0. Okay? And we can see that we have three unknowns and two equations, and dimension of null space is, because the solution of these will belong to null space, right? As we said. So, and what's the dimension of null space here? 1. Yes. So I can assume V3 equals to alpha, and then V2 equals to minus alpha, and V1 equals to alpha. Simple algebra, you are not able to do it. So many people are struggling even to put the simple algebra, nothing else. So what is the V bar greater than? Alpha into 1 minus 1. Okay. So V bar belongs to the null space, and quite obviously you can see that V bar is not 0. And here the condition of the solution is, you know that if A equals to B, our adjoint problem is S star B equals to 0, and if inner product VB equals to 0, then only you get the solution, and that will be the solvability criteria. So I will delete this part, and let's complete the problem. Let's complete the problem. So AU equals to B is solvable, if A equals to B is solvable, if inner product BB equals to 0. If inner product BB equals to 0. Okay? So what is B? B vector is B1, B2, B3, and B vector is alpha 1 minus 1, 1. Okay? So what did you get? What did you get? Inner product BB equal to 0. What did you get finally? What you are getting? Some equation you get. What is the equation? Pardon? Please. Yeah. If there's no right hand side, nothing. Yeah. If you don't say that, that's the problem with your case. We will say only half done, and alpha should be actually cancelled out because it should be B1 minus B2 plus B3 equals to 0. B1 minus B2 plus B3 equals to 0. And that means what? That means we need to have two things actually fixed, right? B1 minus B2 plus B3 equals to 0. That means unless you fix either B1, B2 or B2, B3, we cannot get the solution. So you can say B3 equals to alpha and B2 equals to beta. And what is B1 then? Beta minus alpha. It's so easy. Even this much also you are taking so much of time. So what is a B vector? Alpha into beta into how much is a B vector? How much is a B vector? Minus 1. And this is 1 also, right? Okay. This formula is clear? Is this clear to all of you? Okay. So you can see that this is the this what's the problem? Any problems there in the B vector? So this is the solubility criteria. And for solubility criteria, you can see B belongs to the range space, and this is the criteria to be satisfied to get the solution. Right? Any question? Any doubts? Confusions? Any questions? Any question here? Any question here? No questions? Okay. So next actually I will be talking about another problem which is pretty interesting. Problem number 6. The previous problem. Consider the non-homogeneous equation. You don't have assignments, right? Yeah, I don't see that. I don't know why you come to the class like this. There's no point to come to the class. You can take the notes from there, I can give attendance also. There's no point to have tough time in the class. Coming early morning is very difficult. You're really enjoying it. Consider the non-homogeneous equation A minus lambda I U equals to B. A is a square matrix of dimension n, and let U equals to Cj phi j, where Cj is the coefficients of the expansion and phi j is the eigenvectors of it. If A is a self-adjoint matrix and lambda equation 1 is not an eigenvalue of A, then obtain an expression for the coefficient Cj in the expansion. What are the solvability criteria for equation 1? Fredholm alternative pair. Next question is, do you work for A for the case where lambda is particular eigenvalue of lambda? Note how the solvability conditions are connected to the eigenvectors of A, and if A is non-self-adjoint matrix, and all those things are there. So how to approach this problem? So this is the assignment problem. I'm not supposed to solve, but I just want to see your ideas. I just want to solve your ideas. to solve this problem. A minus lambda I u equals to b, where u can be expressed, I am writing in our own language, these are the eigenvectors phi n. So u can be expressed in terms of eigenvectors. U can be expressed as eigenvector. What is the adjoint problem for this case? What is the adjoint problem? A star minus lambda I b bar equals to 0. Remember that there are two cases here. If lambda is the eigenvalue, then v is the eigenvector. But lambda may not be eigenvalue. In that case, if lambda is not the eigenvalue, if lambda is not the eigenvalue, determinant of A star minus lambda I may not be 0. Right? If V is the eigenvalue vector and if lambda is the eigenvalue, definitely determinant of A minus A star minus lambda has to be 0. But if lambda is not the eigenvalue, the determinant is non-zero and V will be non-trivial. So in that case, what actually happens? Your solubility criteria is inner product B equals to 0, which can easily prove if A star if lambda is a particular eigenvalue. So if lambda is the particular eigenvalue, so definitely this is the solubility criteria. Okay, and it is completely you are completely getting. If it is not, then definitely we will get V is non-trivial and such that inner product VB equals to 0. Okay, so what is the solution then? How to get the solution for this case? Solubility criteria will be done, so no problem. What is the solution? How to get the solution here? We will summation alpha I phi n. What is the solution? What is the solution? Any idea? Hot bench? I have done in the last class. Yeah. So you don't go to the notes. That's what I'm telling you. If you don't go to the notes, then I will come here, talk to myself and go to the class. Is that okay for you guys? Because I cannot work hard for you because my health will get affected if I work hard. And it of no use because I know that 10 or 20% of MTech guys will leave the program. That I know. Because we will be writing GATE exam next year. I will tell you how to read this program. You will write the GATE exam next year. And if you crack the GATE, then you will get the IOCL job and all those jobs. We are here, we have come for time pass. Okay? Of course, I can also say that I am also coming here for time pass. But I am not doing it. I am asking you a question. If you come here for time pass, I won't disturb. I will talk to only some 2-3 students and go. That's it. Why unless I do trouble myself? I should not. Masuda, any questions? How to? I have done it last class. If you can pick up on that part.
We multiply u summation phi and u with a. So a summation alpha I phi.
We multiply not. I am not using that thing. Anyway, I can talk like that, like you in the class. You don't like it, and you say bad teacher, and I cannot say my students are bad. That's the problem. Always, the teacher can be bad to the students, but teacher cannot say students are bad. How to approach this? How to get you? That's what I am asking. Very simple. I have done last class. Very simple. How to get you? We have done in the last class. How to get inner product with this? It is like a case where I said that without solving how to get solution. Right? Without solving how to get solution, that's what I'm asking. If this is the kind of situation, I don't know what I'm teaching in the class, because simple thing, I'm not able to get the answer. Like, I know that my solution is summation alpha is phi I bar, where phi I bar the eigenvectors, and alphas I have been determined with, and I have discussed in the last class how to determine the alpha I. Yes, madam, you are saying something. Yeah. So A minus lambda I u equals to b, and we know that A minus lambda I is summation alpha I phi I equals to b. Am I correct? I equals to 1 to n. And next step. Next step, yes. Okay, summation I equals to 1 to n alpha I a phi I, then minus summation I equals to 1 to n lambda alpha I phi I equals to b, and my eigenvalue problem is a phi I equals to lambda I phi I. This is my eigenvalue problem. So this will be summation I equals to 1 to n alpha I lambda I phi I bar summation I equals to 1 to n lambda alpha I phi I equals to b. Next step. Next step. Next step. First case is symmetric matrix. Matrix A is symmetric. What are the phi i's then? If matrix A is symmetric, what is the function on phi I? Orthogonal. They are orthogonal. So that means if I take inner product with respect to phi I, what will actually happen? Others will be except phi 1 and phi I will be remaining. So alpha I, lambda I, phi I minus lambda alpha I, phi I equals to inner product b phi I, right? Yes? Yes or no? Because summation will go because other terms, for example, if I take inner product with respect to phi 3, for example, so it will be alpha 1 lambda 1 inner product phi 1 phi 3 plus alpha 1 lambda 1 inner product phi 2 phi 3 plus alpha 3 lambda 3 inner product phi 3 phi 3. Only that term will be remaining, others will be going to 0. So only this term is there. Similarly, lambda alpha phi I, other terms will be going to 0 and b phi I. So your solution is what? Alpha I equals to alpha is both the terms is there. Alpha equals to I don't know what kind of things are going wrong. I am not getting any answer from you guys. I don't know what I am teaching also. But also they are finding so difficult to get alpha I. Why so much of time? It should not be in even 1 minute. Yes.
B phi I, inner product b phi I.
Inner product b phi I divided by lambda I.
Inner product phi I.
Inner product? What are you talking about? Boss.
Minus
I'm really surprised what level of mathematics you have and what level of mathematics I may be having some very bad mathematics level. So that's why I'm not able to get it. And it says that alpha I is non-zero if lambda I not equals to lambda. So this is valid if lambda is not equal to lambda. If lambda I equals to lambda, then what actually happens? So this is valid. So whatever solutions you got, so this is interesting thing. That in the question, if you see that if lambda is not a particular eigenvalue, this is a solution. If lambda is a particular eigenvalue, so what actually happens that in case if lambda is a particular eigenvalue, how to get the solution? This is not the proper way. So for example, my lambda is 3 eigenvalue. I may have a minus 2i U equals to B. Yeah, I'm still okay as long as 2 is not my eigenvalue. If I am having A minus 3i, I cannot have this because alpha will not be deterministic. It will be having undefined coefficient. So how to get the solution for this case? If A minus 3i equals to B. So this solution procedure we have done for lambda I is not equal to lambda. If it is lambda, how to get the solution? How to get the solution? I have done in the past rehearsal. Well, 3 is on particular eigenvalue. How to get solution for, because you cannot apply the same technique here because you will get this. How to get the solution? I have done today in the class, today morning. Yeah, it is the problem. Lambda is the eigenvalue. I want the solution. How to get the solution? What is how to get B? You are not talking. You are not telling. You are not talking about the adjoint system. What is my adjoint problem? A star minus 3i bi equals to 0, and we are the eigenvectors. We are the eigenvectors of A star matrix. Vi is because A star has the same eigenvalue. Okay, because we have proved it. Transpose and the thing is same determinant same eigenvalues. Okay, and get symmetric matrix also. It has only symmetric matrix. So what actually happens that this is my solvability criteria. Once it is matched, I can get the solution. Okay, of course we will get infinite solution because determinant of A minus 3i equal to 0. Here we won't get infinite solution because determinant of A minus lambda may not be 0. It will not be 0 if lambda is not eigenvalue. So this is the ways and how to get the solution to the one problem. Problem number 7 we have discussed how to get the solution for this case. We will get the equations for B, and from there you get the range space and you get the solution. Honda is clear for this. I think I have solved almost all the problems in the assignment, and other problem part of the assignment problem you can really work on. For example, you can work on the first problem, second problem, third problem, the Cauchy source inequality, the alpha equals to alpha by theta, and then I also asked you to do the definition of inner product space, how to get the norm definition, and then finding the eigenvector. So everything is done essentially in the assignment. So now we will be talking in the new part of the mathematics, which you have to be seeing first time in your mathematical world. So what I am trying to do it here. I am trying to introduce. So earlier we have seen Ax equals to B, and we have done enough how to solve it. Now we will be doing slightly different. We are going to this kind of a vector space problem, and the question is algebraic system. Can we have differential system in the vector space? Answer is yes, and the kind of problem what we are going to look at is dx equals to x. We are trying to look at dx equals to x. Okay, a differential system. Where is the application of this kind of system? Always you go for the application. Ax equals to b, we got tremendous application. We have seen in process calculation and many of the algebraic systems. Okay, I have shown even enough equation, even process flow sheeting and process calculation and chemical as a chemical engineer. You can have enormous application of Ax equals to b. Whatever we do in mathematics, it should have application, otherwise there is no point to do mathematics because we are doing mathematical methods in chemical engineering. Where is the application of dx equal to x? Which subject? Chemical reaction engineering. Chemical reaction engineering. So now we can see that what are mathematical rich subject chemical reaction engineering is. So actually, in fact, we are lucky that if you are in mechanical engineering, you don't have this kind of system quite often. You can heat transfer a lot because this kind of vector differential equation is called vector differential equation, which is not available in other subjects, and chemical reaction engineering play a key role. So let's talk about some. I will think before getting into much of this, I will be talking on applications. So first we'll talk about the batch reactor. First we talk about the batch reactor. And what is actually happening? A is going to be, and we have the rate expression minus dCA dt, which is a Kc. Okay? This is the first order differential equation, only one variable. Now I will be going to slightly complicate it. A is going to be K1, B is going to Q, rate constant is K2, and C is going to R, rate constant is K2. Okay? So how to write this? You can write minus dCA dt equals to K1C. You can write minus dCB dt equals to K2C, and minus dCC dt you can write K3CC. So this minus you can actually transfer here and you get the system. Now you see what is my X vector here? If you look at my X vector, oh, I'm sorry, I did it, no problem. My X vector is CA, CB and CC. So now I want to express in terms of base dt equals to Ax, and what it should be ddt of CA, CB and CC, and we have CA, CB and CC, which is 1, 0, 0, 0, 1, 0 and 0, 0, 1 minus sign. Okay? So, and of course I write K1, K2 and K3. It's a diagonal matrix. So we can see that this type of batch reactor, this kind of reactions going on, first order parallel reactions going on, first order parallel reactions, and you get associated matrix which is nothing but diagonal matrix. Excellent thing you have seen. So you have seen that dSdt Ax, that A matrix to be diagonal if the reactions are parallel and they are independent. Okay? Each reaction have different reactant, different product. If each reaction, different reactant, different product, that means this guy is not coming this reaction, this guy is not coming this reaction, and the matrix A will be the diagonal matrix, right? Now what will happen for the a bit complicated system? So let's look at the kind of reaction which is having the both sides. We're going the forward and backward reaction. If you have the forward and backward reaction, what will happen to your differential equation? So let's look at that part. So A plus B, I'm now introducing this type of concept, P plus P. Okay, what is this kind of reaction? Autocatalytic reaction, etc. Now you can see what kind of mathematics involved in autocatalytic reaction. So we have dCA, so it is K1, you can write K2, you can write, and you can write dCA dt equals to, what should I write? Minus K1 CACB plus K2 CPCB. Similarly, dCB dt equals to minus K2 CACB, sorry, K1 CACB plus K2 CPCB. The point is this equation, we cannot write because this will give nonlinearity. So dSdt equals to Ax can be written if we have linear system. If you have linear system, you can definitely write. But then we can actually say that then it has got limitations. But I will now discuss one interesting problem where this can be applied tremendously, and which is the Wien-Ratner reaction. Have you heard about this reaction? Wien-Ratner reaction. Wien-Ratner reaction. Go to Google and go to the book. Which book you are following for the chemical reaction engineering? Fogler. Okay. Frome and Bishop, you can see. Have you heard of the book by CRE by Frome and Bishop, F-R-A-O-M-E-N-T. Frome is German guy. Frome and Bishop. That's a book which I used to follow in my PG level when I did my chemical reaction engineering. So Fogler is a good book, but Fogler has a definitely, you can look into the Fogler's book and you have the Wien-Ratner reaction. So what is the Wien-Ratner reaction? You have seen it in chemical engineering. Did you see this kind of reaction? Did you see? This reaction will be there, definitely, I am sure. This is there in Leonard's field also. This is called a Zuiker reaction. So what actually happens to this reaction? A1, A2, and just right becomes a parallel reaction, and A3 going to A1. So it is A21, A12, A32, A23, A31, A13. These are the red constants. What I am asking, is it possible to have dxdt equals to ax here? Answer is yes. What is that? What is the Ray matrix? What is the Ray matrix here? So it is possible to write dxdt equals to ax, and x will be ca1, ca2, and ca3. What's your Ray matrix? What's the Ray matrix? What's the Ray matrix? What is the Ray matrix? Your first row, can you please complete? First row, can you complete? K1 is not there, boss. K2 and K1, K2. 0 will not be there. Minus K21 plus minus K13 plus K13. Last will not be there. You see the thing, what I am writing here. Minus what? What is that? What will be? Minus K2 is already there. Last will not be there, no? Minus, okay, dCA1 dt, what is that? dCA1 dt is coming from here and also from here. Okay, what is that? Minus K21 plus K13 in brackets. That's what I said, minus something. Yeah, that's what. People are saying plus, I don't know why. Is it okay? Is it okay? Okay, next. What is that? K1, okay? K? Okay, next. What is that? K21, okay? Boss, I am doing simple chemical reaction. There is no mathematics here. I am very surprised. Chemical reaction you are struggling. I am not doing any mathematics anymore here. Simple chemical reaction doing here. Minus K12 K 32. Next. 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 Next is what? Next. dCA3 dt. From there it will be coming. K13 K32 minus K23 minus K3. So if you look at this matrix in general you can say that this could be non-symmetric matrix. But the matrix could be symmetric if it is K1 equal to K1 and K1 equals to K1. Okay? And similarly K3 equal to K2. So this system of reaction is actually giving the beauty of mathematical matrix, a beauty of matrix where a matrix could be non-symmetric, could be symmetric. If it is symmetric, you can see that the rate constants, if they are actually same, this matrix could be symmetric, and you can get a lot of interesting episode on that. So I will end here today, and next class I will be discussing more on the solution of dx equal to ax. So we have seen the application of chemical reaction engineering, and we will discuss more on the solution of statements. Thank you very much.